Hello everyone, my name is Nassim Douche. I'm with Mahidol University in Thailand, and I'm going to present the results of a data analysis study at Siriraj Hospital, pictured here. This is the foremost and largest hospital in Thailand. My co-authors for this work are clinicians and administrators from various medical specialty departments at Siriraj, whose names also appear on this slide. In this study, we are interested in analyzing and modeling hospital length of stay. So after a brief overview of the literature, I will present the data used in this study and the empirical properties of length of stay that we have observed and that have consequences for resource planning and finances. And then the model we propose, which is based on the beta geometric distribution. Length of stay is defined as the difference in days between the discharge and admission date of a single hospitalization. We will call this the length of stay per admission, but we'll also slightly abuse this definition by considering the cumulated length of stay per patient, which will be notably useful to study the effect of readmissions and multiple admissions. You should know that Siriraj Hospital is both very reputed and affordable, and so it faces very high demand that often exceeds capacity. It's not uncommon to have waiting lists of several months for admission in some departments. Therefore, it is important to understand the statistical behavior of length of stay and have good models for it, both for resource planning as well as the equity of access to healthcare for patients. To get a feel for the type of statistical behavior that length of stay has, I have these two graphs representing the length of stay for 17,000 admissions and 5,000 patients in the surgery department. On the left-hand side, we can see that extreme observations that are 10 or even 20 or 30 standard deviations away from the mean are not uncommon. There's also a bias where older admissions have longer values than more recent ones. This bias, which we can find in virtually all length of stay data sets, is simply because data have to be collected between two set dates, so there are potentially very long stays that are still in the system. This can be corrected easily by considering the length of stay so far instead of the difference between discharge and admission dates. I should also mention that long stays are periodically reviewed and shortened, so there are active interventions to shorten length of stay, and it would exhibit even more extreme values if it were allowed to naturally run its course. In the graph on the right-hand side, we have the observed maxima over time per patient. We can see that previous maxima are constantly exceeded. And so this makes us suspect that length of stay behaves more like the wealth of a person than, say, the height or weight. It is what's known as a heavy-tailed random variable. For this type of random variables, the mean or median, which are commonly used as performance metrics for length of stay, can be uninformative. Moreover, higher moments like the variance, skewness, and kurtosis may be slow to converge and hard to estimate empirically. And so our main point in this work is that extreme values cannot just be discarded as outliers, which is something that is nonetheless commonly done. They are an essential component of the distribution that determine many of its statistical properties, and it is important for a statistical model of length of stay to be able to reproduce these properties, not just show a good fit or R-squared. And so we'll propose a beta geometric model that reproduces these properties and shows a good fit with empirical data. I will now present some common ways in which length of stay is modeled in the literature, as well as their known limitations. Keep in mind that these assumptions are non-exclusive and can be combined in some models. First, it is common practice to divide data by what's known as diagnosis-related groups, or DRGs, such as asthma or diabetes, and then have a different statistical model for each DRG. There are 467 such groups, and they have been specifically created to have homogeneity in data. This is notably useful to study the clinical factors influencing length of stay and support clinical decision-making. But by design, this approach results in smaller samples, which may indeed make extreme length of stay values appear as neglectable outliers. For larger scale decision-making, such as resource planning in a specialty department, or the hospital as a whole, it is far from trivial to aggregate the results of these different statistical models, and the simplifying assumptions and errors made by each model may accumulate. Perhaps as a result of the division by DRG, another common practice is to use a Poisson, exponential, or Gaussian model. In other words, a thin-tailed random variable. This is often done for the purpose of linear regression. Sometimes this assumption is implicit through the use of z-scores to discard outliers. These models have led to some passionate debates in the medical literature. You can find an example in the paper I have cited here. They also raise the question of what are considered outliers. A commonly used threshold is to cut the top 2% longest length of stay, which has been qualified as somewhat arbitrary. An even more severe issue with trimming outliers is that it may discard important statistical information about length of stay, as I will attempt to show in this presentation. One last family of models for length of stay use mixtures of thin and heavy tail distributions. For example, a Poisson for short stays and log normal, that is the exponential of a Gaussian for long stays. Although they may show a good fit with empirical data, the problem with these models is that they are not supported intuitively. Length of stay is, after all, a discrete random variable, and the log length of stay does not have any intuitive meaning. And they may also overfit and be hard to generalize. For this study, we relied on complete health records for 46,364 admissions at Siriraj Hospital over 4 medical specialty departments. These are surgery, OBGYN, Pediatrics, and Rehabilitation Medicine. As previously mentioned, we are interested in both the length of stay per admission as well as the cumulated length of stay per patient. Here we have some descriptive statistics. The mean and medians globally correspond to international benchmarks, but we observe a very high kurtosis in the first 3 departments, which indicates that the mean and variance don't tell the whole story about the shape of these distributions. As we'll see throughout this presentation, Rehabilitation Medicine is the standout department with a thinner tail distribution. These box plots allow us to visualize all the information that will be discarded if we divided data by DRG and trimmed outliers. In surgery, OBGYN and Pediatrics, there isn't much of a box, in fact, and we can already eliminate the thin tail distribution. Rehabilitation Medicine is once again the standout department, though it still shows extreme values in significant proportions. One quick thing to note about Rehabilitation Medicine is that the value length of stay of 20 days is overly represented in the distribution as a result of hospital policy. Patients are typically discharged after 20 days, save for some serious exceptions. So for once, this fits the textbook definition of an outlier as an observation that differs significantly from other observations. Let's now look at some empirical properties of length of stay that we want a model to be able to reproduce. First, the heavier the tail of the distribution, the more length of stay tends to be concentrated among a minority of patients. Here I have reversed Lorentz curves showing the percentage of length of stay that is consumed by the top percentiles of admissions in orange and patients in blue. The difference between the two curves allows us to visualize the effect of readmissions and multiple admissions. Length of stay in Rehabilitation Medicine once again has a repartition that is close to that of a Poisson distribution, but we observe more inequality in the two other departments. For instance, in surgery, 4.2% of admissions and patients concentrate 30% of length of stay. And in pediatrics, 6.7% of patients concentrate 50% of length of stay. Of course, some patients require more care than others, so an equitable repartition is neither natural nor desirable, but this can be useful to define the thresholds for what are considered long stays, rather than a rigid definition as, say, the top 2% of patients. The elbows of these curves allow us to dynamically define the thresholds, which can be useful for patient reviews. Another thing we looked at is the relationship between length of stay and revenue. Here we have the average charge per day as a function of length of stay. We can see that for rehabilitation medicine, this relationship is increasing, though there is an inflection point at 20 days, after which the rate of increase itself decreases. But the more one stays in this department, the more they are charged per day. It's a whole different story for the other 3 departments. Revenue per day sharply decreases past the first day of hospitalization and has this L shape, as you can see. This means that there is an important opportunity cost to long stays that is not adequately priced currently. Long stays not only mean that you charge less per day on average, but also that the difference in revenue compounds over more days. Compare, for example, admitting 1 patient with n days of stay versus n patients, each staying 1 day. From the standpoints of both equity of access to healthcare and the value provided to patients, this opportunity cost of long stays should be reflected in their pricing. We can think, for example, of differential pricing models such as the ones used in the airline industry to adequately cover this opportunity cost, and provide beds to patients who value them the most when demand exceeds supply. The previous observations raised the question of whether charge and length of stay influence patient outcomes. So we looked at the relationship between average charge, length of stay, and discharge status in surgery, OBGYN, and pediatrics. Here we divided admissions into positive and negative outcomes and tested whether the distribution of charge and length of stay is the same in each group. We found roughly the same distribution, so in brief, we cannot claim that staying and paying more leads to better patient outcomes. For rehabilitation medicine, all patients but one had positive outcomes, so this analysis did not apply. The preponderance of very high length of stay values in at least 3 departments raises the question of the existence of moments, or at least their slow convergence that would require extremely large datasets to estimate empirically. This can possibly make the estimation of indicators such as the mean, variance, skewness, or kurtosis impractical. We use some graphical tests from the extreme value theory toolkit to verify this. In brief, the moment of order P exists and can be estimated empirically if the ratio of the maximum to expectation of the Pth exponent tend towards 0. We have max to sum plots that show the convergence of the first 4 moments here, represented with different colors. For rehabilitation medicine on the left, we see that length of stay per admission has a behavior that is relatively normal, but convergence starts becoming problematic when aggregating data per patient. For the 3 other departments, we have a behavior that is similar to that of a subexponential random variable, and it is exaggerated when considering length of stay per patient. We see, for example, that in surgery we have convergence issues starting from the second moment, that is the variance. Another test from extreme value theory concerns the behavior of the so-called mean excess functions. That is the excess expectation of a random variable over a threshold A as it is defined here. For length of stay, that represents the residual expected length of stay of a patient, conditional on having been admitted for a certain number of days. For a thin-tailed random variable, such as a Gaussian, as we have in the blue curve, this function is decreasing. For example, the life expectancy of a vehicle would have this behavior. The higher the mileage of the vehicle, the lower its residual life expectancy. A constant mean excess function is characteristic of a memoryless random variable, such as the exponential in the red curve. The perturbations you see at the end of the curve are known as the finite sample bias, and it's common to omit observations at the extreme right. Now, an increasing mean excess function, which we can see in a Pareto and a beta geometric in green and black, are characteristic of heavy-tailed random variables. The longer an observation has been made, the longer it would be expected to remain. For example, technologies have this property. We can expect the pen to still be around long after the smartphones, and the spoon as a technology even longer than the pen. These things age in reverse. With length of stay, we can observe that the 3 departments in which we suspected heavy-tailedness show an increasing mean excess function. This may sound counterintuitive, but it's not really the case. Knowing that a patient has already been admitted for a certain time, you would expect their condition to be all the more severe, and thus their expectation of remaining admitted to be all the higher. And there is a surprise in the rehabilitation medicine department, which is an increasing mean excess function past the 20 days threshold, meaning that if a patient hasn't been discharged by that time, the residual length of stay would be increasing. So this means that, save for manual restrictions imposed on it, length of stay is naturally heavy-tailed in this department as well. These effects are exaggerated once again when aggregating data by patients, and we find a linear mean excess function in surgery, which is commonly associated with Pareto distributions with exponents higher than 1, which cause convergence problems even for the mean. So based on the previous tests, we posit that length of stay is a subexponential variable. These variables are characterized by the property described in this slide. Intuitively, this property implies that for 2 observations, the value of the sum, if high, tends to be dominated by an individual observation, the other one contributing negligibly. For length of stay, if I tell you, for example, that 2 patients have a very high cumulated length of stay, it is likely that only one of them has very high length of stay. This is not the case, for instance, for two people with a high cumulated height or weight. It would likely be the result of both of them being tall or overweight. The beta geometric is a discrete compound distribution that can be used to model a wide variety of tail behavior, depending on its underlying parameters. In addition to its discreteness, it is supported by natural assumptions to model the length of stay. If we assume that upon admission a patient has a probability P of being discharged any subsequent day, what we get is a geometric process, that is the number of trials before a success. Within a healthcare unit, it is reasonable to assume that different patients have different probabilities of discharge. So if we assume that P itself is a random variable, and the beta distribution is typically used to model random real numbers between 0 and 1, what we get is a beta geometric process. That is the number of trials before a success in a population with heterogeneous probabilities of success. Here we have the probability distribution function of the beta geometric. You can see that it's defined by two parameters, alpha and beta. Now, this random variable can exhibit tail behavior that ranges from thin-tailed, after all, the geometric is a particular case of the beta geometric, to the most extreme heavy tails, as illustrated with the mean excess functions and max to sum plot on the right-hand side. These have infinite moments. The beta geometric also verifies the property of subexponentiality, as we have previously defined it. And you can see it with the convergence of the previously defined ratio to 2 in the graph on the left-hand side. It is possible to compute the maximum likelihood estimators for alpha and beta, the two parameters of the beta geometric, by maximizing the function described in this slide with respect to empirical observations. And this can be done using statistical software packages. So we have fitted the maximum likelihood beta geometric to the empirical data in surgery, pediatrics, and OBGYN, and it showed excellent fit with respect to the Kolmogorov-Smirnov test. And importantly, it reproduced the properties that we have previously observed. Here is what we got in surgery, for example. For rehabilitation medicine, things were a bit more delicate. Length of stay in this department is most likely of a mixed nature, because of the manual restrictions imposed on it, as we have seen, that make 20 days so preponderant. So here we have used the mix of Poisson for stays below 20 days and beta geometric for stays above 20 days. The fit wasn't as good as for other departments, but it was still decent. Mixed distributions is still an understudied problem outside Gaussian mixes, so this is one area for improvement. So in conclusion, I would say that extreme values determine many important statistical properties of length of stay. They are not to be discarded as outliers, which is something we may not see when dividing data by diagnosis-related group. We have also seen that the longer a patient has stayed, the longer their expected residual length of stay, with a corresponding increase in the opportunity cost of long stays. We have highlighted some practical difficulties in estimating the moments of length of stay from empirical observations due to the slow convergence of the law of large numbers. And we have illustrated the importance of reducing unnecessary readmissions and avoiding multiple admissions. As they compound to make the tails heavier, they exaggerate the previous challenges. Now, seeing hospital admissions as a simple geometric process with heterogeneous probabilities of discharge adequately reproduces these properties and provides a good fit with empirical length of stay. So I thank you very much for your attention. If you would like to have more details about this study, we have a preprint on medRxiv, and you can find the URL on this slide. Thank you.